So for Loregian, we talk about a few remarks on the fibrations of algebras. So please, Fosco.
Yes, thank you. So first thing first, this is a joint work, a work in progress, and hopefully joint work with Greta Coraglia and Davide Castelnuovo. They are here in the audience. Actually, I have to say that this talk is stress even more that this is a work in progress. Actually, my talk is a question for the audience. Our talk is, our work is a question for the audience, because essentially we need help to finish this soon to be or hopefully paper that contains good ideas, in my opinion, but doesn't have a punchline. So the talk will end without a punchline. Sorry, apologies in advance. So let me start with the motivation, why we started asking some questions. And actually, there is a very simple example that motivated us. If you start studying fibrations and categorical logic or in other parts of category theory, you very soon meet this construction that is called a simple fibration. If you fix a Cartesian category, you can build a category over it that has a typical fiber over an object, a category that has the same object of the base, and a map, a morphism in the fiber between x and y over an object I is just a morphism between x times I and y. Composition inside the fiber is this complicated to parse expression that defines this category that is called, each fiber is called a simple slice over I. But, you know, category theory is about having conceptual looks on things, so it's good to know that this category, this fibered category over C arises from a universal construction, because every functor that, every end functor of C, of a Cartesian category that sends A into A or X in X times I is a comonad, because the category is Cartesian, and the simple slice, C slice I, is the Cook-Kleisley category of this comonad. So, and composition that before was quite mysterious to parse is just Cook-Kleisley composition. So, good to know, because this fibration arises from a certain universal construction as a fairly simple universal property. Well, if you start playing the same game with the same comonad, but instead of taking the Cook-Kleisley, you take the whole category of coalgebras, then you get the slice. So it's even better, because now we have a universal meaning for an even more straightforward category, the domain fibration over a Cartesian category. So when we started thinking about how to generalize, how to encompass this in a general theory, we had essentially three questions. Can we write down a theory of this kind of constructions? Can we lay down a foundation for the categories that arise from these and similar constructions? Can we find more examples? And in a posteriori, the answer is yes, we can say something, and there are many examples of these things arising from type theory, categorical logic, algebraic geometry, homotopy theory, pure category theory, really, you name it. And maybe even more important for applications and for finishing the damn paper is the simple fibration as a fairly straightforward but nice type theoretic interpretation. Can we find a similar type theoretic meaning for fibrations that arise from parametric endofunctors? Because this is what we are out and about. So this leads to the definition of what is the fibration of algebras and fibrations of algebras more in general. We want to study and classify fibrations that arise from a parametric functor, a parametric endofunctor. I will never bother separating notationally a functor from a category A of parameters into endofunctors of X and the mate of that. I will call them the same name. And for each f of I is an object of the category of parameters, we consider the categories of algebras. We stitch all these categories together, as is customary in fibration theory. Well, we get a contravariant functor from A to the category of categories. This induces a fibration, and this is what we want to study. We want to find examples and theorems that are valid for this kind of functors. So a starting point is to recognize that each fibration that arises in this way is the pullback of a universal fibration of algebras. This functor is from over the category of endofunctors of X and has domain a category alg that essentially has over an endofunctor. There is the whole category of algebras for that endofunctor. Algebra now has to be intended very broadly because I can consider endofunctor algebras or co-algebras. I can consider Eilenberg-Moore categories of monads or co-Eilenberg-Moore of comonads, Kleisli or co-Kleisli. So I want stuff that I can functorially attach to an endofunctor of any kind. And a first remark is that every property of U, this universal fibration that is, well, every property that U has and which is pullback stable is inherited by all P of F fibrations that we want to study. So this was a good starting point. There are properties of this U that can be bookkept and so are inherited by every P of F. And we were fairly happy. Now, let me make precise what I mean by algebras, because I say that the term is very broadly intended. You have a U where the fiber over F is the category of endofunctor algebras, where F is a mere endofunctor. But if F is pointed, you might want to have as fiber the category of pointed endofunctor algebras, where the structure is compatible with the unit, with the pointing. And if each F of I is a monad, well, it's fairly natural to ask that you have as fiber the Eilenberg-Moore category. Of course, you can dualize. You can do the same thing, dualize. Co-pointed, co-Eilenberg-Moore. Just be careful that the morphism change because you have to require more and more as you filter out the algebras that you want. So if P appears in a pullback for any of the previous choices, we call them we call it a fibration of endofunctor algebras, a pointed algebra fibration, or an Eilenberg-Moore fibration. And of course, again, you can dualize. You can talk about co-algebras, endofunctor co-algebras, co-pointed co-algebras, co-Eilenberg-Moore. Just be careful that the case of Kleisli and co-Kleisli has to be treated with a little bit of attention, because on the surface, one would like to say that you have a map of fibrations between Kleisli of T and Eilenberg-Moore of T arising from the... But the problem is that these maps do not assemble in any meaningful way into a map of fibration, or let alone a natural transformation, because Kleisli is covariant and Eilenberg-Moore is contravariant. Now, you could and should say that this is a denatural transformation, but then why bother? In the end, it doesn't seem that this map has any very interesting property. It's not, if I remember well, it's not even fibered over endofunctor. So the case of Kleisli categories, well, I mean, you have to treat it as a per se case. What is more important is that we have plenty of examples now. Certainly we recover the example we started with. The co-Kleisli fibration of this very simple comonad gives you the simple fibration. The domain fibration is the category of is the co-Eilenberg-Moore fibration of the same comonad. But, well, a first new example that is not really new, because this category is a very old friend of geometers and algebraic topologists, when we consider the same endofunctor, but now the parameter is a monoid, this endofunctor product with A is a monad. It's a fairly simple example of a monad. And the algebras now, for this monad, the Eilenberg-Moore category, is the category of objects with an action of the monoid. So we recover from starting with a fairly logic-oriented motivation, with a quite abstract motivation, something that is well known in algebraic geometry, because this fibration of algebras where the fibers are modules over a ring is very well known and very well studied. Also in computer science, other people took this idea. So we recover it. We can play the same game with topologies if you want, because if we fix a set and it's poset of topologies, then there is a fairly tautological correspondence that sends a topology into the category of sheaves for that over that topology. And this is a fibration of our kind, essentially because, well, sheaves is reflective into pre-sheaves, and this is a idempotent monet. So we can consider these reflective subcategories as the categories of algebras for idempotent monads coming from sheavification, where the parameter is an element in the poset of topologies over a set. This looks an overly complicated way to state something simple, but you can play the same game with Grothendieck topologies. And even more important, you can play a similar game, or you can put in a similar framework an old idea of Kelly and Lovier that if you fix a topos E, then the class of all its essential localizations is possesses some structure. It's a complete lattice. And then if I play a similar game with what Lovier and Kelly call levels of the topos, I can obtain a category fibered over these complete lattice, which is the lattice of levels of the topos. So you see, these examples have a topological instead of a type theoretic or algebraic. I can consider also polynomial functors, because the way polynomial functors are built often, very often depends on a parameter. We can describe classical polynomial endofunctors in the way Moerdijk and Palmgren described in their joint paper on polynomial functors. In this fairly simple way, if you fix a locally Cartesian closed pretopos, that's enough, and an object of the slice over an object over A in the pretopos, there is a polynomial endofunctor that is built from the functor from E, the section of the domain fibration, and in the middle you put homing with F for the internal home in the locally Cartesian closed pretopos. We can study more modern versions, more modern flavors of polynomial functors, because Gambino and Koch devised this notion, this very elegant, very general notion of polynomial functor that depends not on a morphism of the slice, but on this diagram. It's not a span, it's not a cospan, it's this shape, and that bookkeeps how the coefficients of the polynomial depend on I, B, and A. And well, each such fractor F is the object of a category, and my category of parameters now is this one, and the endofunctor that I obtain is over the slice on I. So it's a very layered construction, you see, but it's an example of something quite simple that we are able to fit in a hopefully bigger framework. So there is hope that this is saying something, although we don't really know exactly what. We can also make a few structural observations about this, and then unfortunately the talk will finish. I say there will be no punchline, but we can try to have a more structural view on this. Well, for example, we can refine with a little bit of knowledge on presentable categories and transfinite constructions. We can say that, well, if the endofunctors have some rank, if I can bound their accessibility rank, the reindexing of the fibration of algebras are all right adjoints. They have a left adjoint. You can build with the adjoint functor theorem done fiber-wise. You can build a left adjoint for each reindexing. And well, there is little to add about this. Of course, this is not our idea. The proof is very simple, and it's based on the usual strategy Freyd uses to use the adjoint functor theorem. The only thing I could say is that this happens a lot, actually, because it happens quite often that the functor that you consider have some access, they have bounded rank. A notable example is from algebraic theories, many algebraic theories, many polynomial functors that have finite, that are finitary. This is a two-dimensional view on what we did, because there is a very two-categorical way to characterize the fibrations we want. Fibration is an Eilenberg-Moore fibration, so every fiber is the Eilenberg-Moore category of a parametric monad, if and only if, in the two category of fibrations, there is a morphism of fibrations from P to the projection, which is a monadic one cell in fibrations over A, which is kind of elegant. If you unwind this criterion, it's essentially saying that H has a left adjoint, which is fibred over, well, that should be, yes, A. And then the Eilenberg-Moore object for the monad that you have from the adjunction L and H is exactly P. So a fairly elegant. This sort of suggests that there is something too categorical, formal going on here. And the proof is not particularly exciting. So, well, there is another way to characterize this, to state this two-dimensional criterion. I don't know if I'm going slightly over time, but this is, well, this says the very same thing, but exploits the fact that instead of presenting the Eilenberg-Moore fibration in the way I said before, this is saying that a fibration is of this kind, if and only if from that we can extract a diagram of monadic categories indexed over the category of parameters. Because essentially this category of monadic functors over X is equivalent, anti-equivalent to the category of monads on X. Good. So another kind of juicy example that we can fit in our framework is that of graded monads. Graded monads are a notable example of a functor that in some sense is depending on a parameter, although in a not exactly the same sense we are talking about. They are vastly used, vastly studied in computer science. And well, the starting idea is an old motto of Benabou. A monad in cat is just a Lax functor from the point to cat, because the condition for T to be a Lax functor are exactly the monad axioms. A graded monad, instead, is a Lax functor from something else, something bigger. In particular, the case that is studied in computer science and elsewhere is a Lax functor from the looping of a monoidal category. You regard M as a one object bicategory, and then a Lax functor from this bicategory into cat will be a graded monad by definition. And you can do, to a fairly large extent, the formal theory of monads for graded monads in this sense. So, and these are, in a very strong sense, endofunctors depending on a parameter. For example, you can say that the object of algebras for a graded monad is exactly the Lax limit of the Lax functor associated. And of course, this is true also for a Lax functor from the point. This is the universal property of the Eilenberg-Moore category. So, can we do something similar? Well, in a sense, yes. In a sense, our story is even more general, because we are doing something similar, but we are not requiring monoidality in the domain, in the category of parameters. And every plane category will do. Every category of parameters does our job. And there is a stark difference in the way, in how we consider algebras, because for us, the starting point was considering all categories of algebras separately. Instead, for graded monads, you consider algebras that have an action of every T of I, where I is the parameter. You fix an object that possesses an action of every T of I, compatibly. So how to solve this conundrum? How do these definitions interact? Well, the point is that there is a bicategory, sigma of A, that you can lift, you can regard the category of parameters as a lifted up version of a bicategory. in such a way that, for example, for Albert-Moore algebras, functors from the parameters to monads and monads morphisms are exactly Lax functors. Oops. Are exactly Lax functors from sigma of A to cat. And the diagram that we have, the diagram of algebras, is exactly a presentation for what the Lax limit of this correspondent f tilde from sigma A to cat is. So graded monads say we have a parametric endofunctor and we have a diagram that presents its Lax limit. We throw away the diagram and we keep the Lax limit. We have both, because we have the diagram, and if we want, we can compute the Lax limits. So again, this is saying there is something under this hood, but now you wonder what's going to happen in the next slide, and we don't know, because we worked about this. You see, we have something, but in our opinion, there is not very much to tell a coherent story, to write a paper about this, to really point out some application, some theorem that we can prove and other people can't. So you see, this is a cry for help, because anyone that has suggestions or can find a better narrative, can provide more intuition about what we are doing, is more than welcome to help us. We have a language, but we don't know where to use it. So it's really, we are desperate. And Greta is nodding because, yeah, we are. So, but anyway, thank you. This.
So thank Porco for his talk, and let's help him and help his host.
But also Greta and Davide. I'm not alone in this mess.
Help the co-authors and Fosco to write this paper. So any comment is very welcome, I think. Here is the rescue.
Thank you. Very, very, very basic question. What is that sigma that's supposed to be the left adjoint in the last adjunction?
Yeah, it's.
Is it like B, or is it the?
No, because it's not exactly the looping of a category into a bicategory. It's I have to check in the notes, because this was done 2 weeks ago. I'm really in the messy stage of understanding.
So it's not the same.
This bicategory is 2 objects, and then
oh yeah, and A is the category of morphisms between.
Yes,
them.
A is the category of parameters, and
just
from A you build this bicategory with 2 objects. And then, honestly, I don't remember, but yes, exactly.
Yes, so if I remember correctly, basically you just have a source object and a target object, and you map objects to maps, and then 1 cells to 2 cells between these, and kind of 2 ways de-looping kind of way.
Yeah. It's a bit tricky, yes. But does this have a name? People more comfortable with? Probably, yeah. It looks like. See why I called it sigma.
2 points of suspension. Say. So, what do you say about these 2 points?
It's used, for instance, in some works of Martina Rovelli and Vittorio Zornova, where they use it to get some property of orientals.
Okay.
And I think they call it 2-point suspension from
But
topology.
then I was right to call it sigma. Yeah. I'm happy.
I think they call it sigma too. Yeah.
Okay, so completely unbeknownst.
So at least we helped for the name of the thing.
Yes, the Rovelli Ozornova construction.
Yes. And so, are there any other questions, comments, or other?
It's me again. So you're commenting here about the, like, it's more general than just an action, right? There's no monodality assumption.
Yes.
But if you have that, can you say something more? Have you thought about this?
Well, if your A is a monoidal category,
but
and then you
F
also
is a monoidal functor. Yeah.
Exactly. That's the point. The graded monads essentially say look, I have a family of endofunctors like this, but then I have the multiplication is not Tm composed Tm into Tm, but it's Tx composed Ty into T of xy, whatever xy means. And in a monoidal category, that's the tensor. So you have a Lax monoidal functor. We don't ask it, we don't require it. But if you do, you recover exactly graded monads.
Yeah, no, I'm familiar with that. No, my question is, so you have this nice, like, you can look at these fibrations of algebras and this very nice, I mean,
Yes.
like if you add this extra thing, do you get extra nice things? Like, for example, like I think the fibration gets monoidal, then probably you pull back a monoidal fibration.
The problem is how algebras are treated, because the notion of algebra for a graded monad is not the algebras for Tx and x stays fixed. The same A as an action for every m in the monoidal category, in the parameters, and the algebra axioms are quantified over all at the m's, which is something that we don't have.
I see, okay.
The problem is exactly, a graded monad is defines a notion of algebras that is the Lax limit of the Lax functor. We don't. We present a diagram with which we can compute the Lax limit. And then we obtain the same thing.
Okay,
That's
you.
the gap.
Thank you, Matteo. And I think that we are still in time, so luckily for the coffee break. Otherwise,
Luckily, yeah.
So, are there
The
any
club.
other question, comment? If not, let's thank Fosco again.